Welcome everyone. During this lecture we're going to derive the conservation of momentum theorem. We'll introduce the three collision types. We'll discuss a single-phase conservation of momentum theorem application as well as a two-phase conservation of momentum theorem application involving a ballistics pendulum. We will begin by deriving the conservation of momentum theorem. To do so, we will consider two bumper cars that undergo a collision. This diagram shows two bumper cars that are about to collide with one another. We labeled the mass of the first bumper car as M1 and the second bumper car has a mass of M2. During the collision, we know that M1 will apply a force onto M2 that's directed towards the right. We will label this force as F21. That is the force on object 2 produced by object number 1. Likewise, the second bumper car will apply a force onto the first bumper car, and that force will be directed towards the left. We will label this force as F12. Again, that's the force on bumper car number 1 produced by bumper car number 2. According to Newton's third law, anytime two objects interact, the force of object 1 on object 2 will be equal in magnitude but oppositely directed to the force of object 2 on object number 1. We can express this as follows. We can state that F12 simply equals the negative of F21. Now, according to Newton's second law, we know that generally speaking, F just equals mass times acceleration. If we apply that to the equation we have on the left, that will produce M1 times A1 must equal the negative of M2 times A2. Now, from the 1D motion equations, we know that velocity equals initial velocity plus acceleration times time. Of course, this is the final velocity. We're going to change the way that we describe these velocities. So instead of v, we will be explicit and term this as v final. Instead of v0, we'll term it as v initial plus the acceleration times the time. Now, we can solve this equation for acceleration by first of all subtracting v initial from both sides. That yields v final minus v initial equals at, and we can solve for the acceleration by dividing both sides by t, and that'll yield v final minus v initial divided by time. Let's now apply this result to both sides of our earlier equation. If we do that, we will obtain M1. Now, instead of A1, we will substitute V final for object number 1 minus V initial for object number 1. So we will term it as VF1 minus VI1. And on the other side, we will replace the acceleration with V2 final minus V2 initial divided by t. Now, since the collision takes place over the same amount of time for both objects, we can cancel the time from both sides of the equation. We can also distribute the mass into the parentheses on both sides as well, and that will result in m1 v1 final minus m1 v1 initial equals minus m2 v2 final plus m2 v2 initial. Now, in order to note that these velocities are vector quantities, we're going to introduce arrows on top of these, because the direction of the velocity is very important within our consideration. What we'll do next is we will separate the final terms from the initial terms by bringing this term to the left-hand side, and we'll bring this term over to the right-hand side. That'll also eliminate the negatives in our equation, so that will result in m1 v1 final plus m2 v2 final equals m1 v1 initial plus m2 v2 initial. This is actually known as the conservation of momentum theorem, and it's important to note that the product of mass times velocity was defined earlier as momentum. So m1 v1 final is just p1 final, which is the first object's final momentum after the collision. This term is just p2 final. On the other hand, we have P1 initial plus P2 initial. This result tells us that if we add the momentum for the first object with the momentum for the second object at the end of the collision or following the collision, that sum will equal the momentum before the collision for the first object plus the momentum that the second object has before the collision. Let's summarize this result conceptually. The conservation of momentum theorem tells us that when two or more objects collide with one another, the sum of their initial momenta will equal the sum of their final momenta. And of course, the word momenta is just the plural for the word momentum. Now, this theorem is based on a condition, and let's introduce it. The condition requires that the effect of all external forces must be negligible. In other words, if we do have external forces present, the effect of those forces on the collision must be considered negligible. Let's now incorporate our earlier results. For two masses, we discovered the following relationship. P1 initial plus P2 initial equals P1 final plus P2 final. That's the general equation. The working equation looks like this. M1 V1 initial plus M2 V2 initial must equal M1 V1 final plus M2 V2 final. This is the working equation, so we will place it inside of a box. And we will also introduce a few important notes. Starting with the fact that all collisions begin and end at the same location. This is a very useful assumption when considering various applications. In other words, we will assume that there's very, very little displacement during the brief time period when the collision is taking place. Secondly, when solving for velocity, a positive answer means that the choice for direction was correct. In other words, we're not always certain regarding the direction that an object will travel following a collision. Therefore, sometimes we make an assumption about the direction. If the result turns out to be positive for the velocity, that means that the choice that we made was correct. Otherwise, it's incorrect. And so, the third note reflects this. When solving for velocity, a negative answer means the choice for direction was incorrect. Fortunately, we wouldn't have to repeat the problem under these circumstances, but we would have to realize that if our choice was a left-bound velocity, well, then the object is actually traveling towards the right after the collision. Finally, the fourth note indicates When an object is traveling toward the right, or upward, the velocity is considered to be positive. On the other hand, when traveling toward the left, or downward, the velocity is considered to be negative. We will now introduce the three collision types. Starting with an inelastic collision. An inelastic collision is one in which energy is not conserved. So where does the excess energy go? It turns out that the excess energy causes permanent deformation and or heat. The second type of collision is called a perfectly inelastic collision. In this type of collision, energy is still not conserved. And the objects stick together after the collision. If that's the case, if they stick together, then they will have the same final velocity. And therefore, V1 final will equal V2 final, and we will just abbreviate those velocities as V final, because there's no distinction between them. Let's now see how this would affect the conservation of momentum theorem. Here's the conservation of momentum theorem, and we're going to substitute V final in place of V1 final and V2 final. When we do this, we may also factor out V final algebraically, and the result will look as follows. M1 V1 initial plus M2 V2 initial will equal M1 plus M2 in parentheses times V final. We will now introduce the third type of collision, which is called an elastic collision. Elastic refers to the fact that energy is conserved. Therefore, an elastic collision is one in which energy is conserved. Now, under these conditions, we may combine the conservation of energy theorem along with the conservation of momentum theorem, and through a fairly lengthy process, we obtain a very useful result. Like I said, the process is fairly lengthy, so we'll avoid it, but let's observe the outcome of that assessment. The outcome of that combination looks like this. V1 initial plus V1 final will equal V2 initial plus V2 final. Now, this outcome may only be used when the word elastic is referenced within a problem. If the problem does not use the word elastic, then this equation cannot be used. So let's include a note to that effect. We will now introduce an application of the conservation of momentum theorem. In this application, a 350 kilogram bumper car, initially traveling toward the right at a rate of 4 meters per second, collides inelastically with a 180 kilogram bumper car, initially traveling at a rate of 1.5 meters per second, toward the left as shown below. Immediately afterward, the 350 kilogram bumper car travels at a rate of 2 meters per second toward the right. If the time of contact between the two cars is 300 milliseconds, we'll begin by determining the velocity of the 180 kilogram bumper car immediately after the collision. Now let's take a look at the initial diagram. This diagram depicts the two bumper cars before the collision, and as we can see, the bumper car on the left is actually traveling towards the right, and M2 is traveling towards the left. Let's indicate the initial velocity of M1 as V1 initial, and it's directed towards the right. Likewise, the initial velocity of M2 can be indicated by V2 initial towards the left. In the final diagram, we're depicting what happened after the collision. So that the collision took place, and as a result, M1 is still traveling to the right. However, M2 has reversed its direction as a result of the collision, and it is now traveling toward the right. So we'll indicate these two velocities as V1 final as well as V2 final. We will now apply the conservation of momentum theorem toward determining the final velocity of the second bumper car. Let's abbreviate conservation of momentum from this point forward simply as COM. The conservation of momentum theorem tells us that if we add M1 times V1 initial to M2 times V2 initial, that will result in M1 V1 final plus M2 V2 final. Let's incorporate the values into this equation. M1 was given as 350 kilograms. V1 initial was given as 4 meters per second. M2 was given as 180 kilograms. V2 initial was given as 1.5, but since the object M2 was traveling to the left initially, we'll enter it as a negative 1.5 into our equation. The right-hand side will equal 350. V1 final was given as 2, and M1 is traveling towards the right, so we're entering it as a positive value. And M2, of course, equals 180. We'll enter the magnitude of V2F as a positive value because we're assuming that the second bumper car travels to the right after the collision. So we'll enter it as positive V2 final. Notice that I removed the arrow because we're only incorporating the magnitude of the velocity. Using a calculator, the left-hand side becomes 1,130, and on the right-hand side we have 700 plus 180 V2 final. Let's subtract 700 from both sides. And the result on the left is 430, and on the right we have 180 times V2 final. And of course, if we just divide both sides by 180, V2 final equals positive 2.389 meters per second. And the positive indicates that we chose the correct direction, so V2 final is directed towards the right. Now I'm specifying V2 final with a magnitude and a direction. That means it's a vector representation, and that's why we will bring back the arrow on top of V2 final. And let's note that the positive means we chose the correct direction. In part B of the problem, we need to determine the amount of kinetic energy lost as a result of the collision. So in part B, we want to determine the change in kinetic energy, which we'll abbreviate as delta KE. Now, in order to determine the change in kinetic energy, we will need to determine the final kinetic energy of the system minus the initial kinetic energy of the system. Now, the system is composed of two bumper cars, so each will contribute to the final as well as the initial energy states. So if we expand this accordingly, KE final could be described by KE1 final plus KE2 final minus KE initial can be described as KE1 initial plus KE2 initial, and we're using brackets because we have to add up the initial kinetic energies and then subtract them from the final kinetic energies. Let's expand this equation. Of course, kinetic energy generally is given by 1/2 mv squared. So if we apply that relationship, we obtain 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared minus 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. And we don't need the arrow because we're only squaring the magnitudes of the velocity. Let's incorporate the values now. So in the first term we have 1/2 m1 equals 350, and v1 final was noted as 2 meters per second. m2 has a value of 180, and v2 final was just calculated as 2.389. And we're going to square that result. Minus (1/2) m1, v1 initial was 4 meters per second squared, plus 1/2 m2 is 180, and its initial velocity was negative 1.5. Of course, if we square the negative 1.5, it becomes positive, so we have the choice of entering it in as a positive. However, if you do decide to enter it as a negative value into the calculator, make sure that you include it in parentheses before squaring the number. Using our calculator, the left-hand side equals 1,213.7 minus, within the brackets, the result equals 3,002.5. And if we subtract those two results, the change in kinetic energy equals negative 1,789 joules. So as a result of the collision, the system lost this much kinetic energy. Let's take a look at part C. In part C, we would like to determine the impulse delivered to the 180 kilogram bumper car. Of course, the symbol for impulse is I, and we want the impulse delivered to the second bumper car, which we called M2. Now, there were two impulse equations that we discussed earlier. The first one looks like this. And the second impulse equation looks like this. And clearly, the second form is more useful to us than the first form because we don't have the force available to us. So let's apply the second form. Now, since we are asked to find the impulse applied onto the second mass, we can customize this equation by noting that m refers to m2 and v final refers to the final velocity of mass number 2, which we called v2 final, minus m2 v2 initial. Let's include the results. m2 has a value of 180, and the final velocity of that mass was calculated as 2.389 minus m2, again, the value is 180, and v2 initial was given as negative 1.5. Of course, it was given as positive 1.5, however, the fact that m2 is traveling toward the left means that the 1.5 has to be entered in as a negative value. Using a calculator, the impulse equals positive 700, and the units are kilogram meters per second, or you can use Newton seconds as the unit as well. Now, what is the significance of the positive sign? The positive sign indicates that the impulse is directed towards the right, and it's delivered by M1, which was traveling towards the right, onto M2. Let's take a look at the final part of this problem. In part D, we would like to determine the average force delivered to the 180 kilogram bumper car. So we need to find F average on M2. This time we're going to use the first form of the impulse equation, because now we have the impulse available, the time was given within the problem. This is the equation that will resolve the force. So again, the impulse equals the average force times delta t. The impulse was calculated as 700. The time was given as 300 milliseconds. Let's take a look in the problem. Here it is. The time of contact during the collision equals 300 milliseconds, and of course we have to convert that to seconds. A millisecond, of course, is 1/1000th of a second, and so to convert this, we'll just bounce the decimal point over 3 times to the left, and that results in 0.3 seconds. And now if we divide both sides by 0.3, the average force simply equals 2,333 newtons. We will now introduce another application of the conservation of momentum theorem using a ballistics pendulum as well as a two-phase approach. In this application, a 25-gram bullet is fired into a 2-kilogram wooden pendulum as shown below. If the bullet becomes embedded within the block and the system rises to a maximum height of 6 centimeters, determine, in part A, the bullet's initial velocity before the collision. So let's examine this diagram. What we're looking at is a bullet that has a very high initial velocity that's about to collide with a wooden pendulum. Once the bullet makes contact with the pendulum, it penetrates the wooden portion of it, and as a result, the block as well as the bullet that's embedded inside of it take off with an initial velocity that we're representing in this part of the diagram immediately following the collision. So again, it's important to note that the collision begins just at the point when the bullet makes contact with the wooden block, and it ends the instant where the block and the bullet begin to take off. As we noted earlier, these two positions are considered to be the same position. What happens after the collision is over? Well, this diagram represents the conclusion of the collision. And afterward, the bullet block system starts to travel upward and attains a maximum height that we've noted by h equals 6 centimeters. Once it attains maximum height, of course, the final velocity of the system equals 0. We have depicted a two-phase problem. The first phase involves a collision, and we can label it between this location and this location as phase A. And this phase is addressed through the conservation of momentum theorem, because this phase involves a perfectly inelastic collision. So we'll note that the conservation of momentum theorem governs this phase. Once the collision is over, as depicted in this diagram, the system travels to a maximum height of 6 centimeters. That portion of the problem is governed by the conservation of energy theorem. So this is phase B, and it's governed by the conservation of energy theorem. So it's important to note the distinction between these two phases. And by the way, the final velocity in phase A becomes the initial velocity in phase B. We will now determine the bullet's initial velocity before the collision, which is represented as V1 initial within our diagram. Let's apply the conservation of momentum theorem. Of course, the theorem states the following: M1 V1 initial plus M2 V2 initial simply equals M1 plus M2 times V final. And of course, this is the perfectly inelastic version of the conservation of momentum theorem. Now, M1 within the problem was noted as 25 grams, and of course that has to get converted to kilograms as 0.025 kilograms. V1 initial is what we're looking for, and we'll enter it as a positive magnitude because the bullet is traveling towards the right. The block is initially at rest, and so its initial velocity is 0. On the other side, we have M1, which is 0.025. The mass of the block was given as 2 kilograms times V final, and notice that I entered the magnitude of V final as a positive value as well, because the system takes off to the right immediately after the collision. And so on the left we have 0.025 V1 initial, and on the right we have 2.025 V final. And if we divide both sides by 0.025, we can simplify the relationship as follows. V1 initial will just equal 81 times V final. That's the result of phase A. We'll call that equation number 1. And obviously we can't solve for V1 initial until we obtain V final, which is the final velocity of the system immediately after the collision. We're now going to apply the conservation of energy theorem by considering phase B of the problem. Now, the conservation of energy theorem states the following: mgy initial plus 1/2 k x initial squared plus 1/2 m v initial squared equals mgy final plus 1/2 kx final squared plus 1/2 mv final squared. Now, we have two masses within this problem, so the question now is, which mass do we use within phase B? Let's take a look. Within phase B, we basically have the wooden block and the bullet moving as a single unit together. Therefore, the mass that we will be using within the conservation of energy theorem is the combined mass of the bullet and the block. So we'll make a note that the mass simply equals m1 plus m2. Now, we need to determine which of these terms equals 0, and we'll do these one at a time. mgy initial. If we look at phase B, the system is at its lowest elevation at the beginning of the problem. And of course, this dotted line is the zero reference height. Since the system is located at the zero reference height initially, it has no initial height, and therefore the first term equals 0. This term refers to the compression or elongation in a spring, and we do not have a spring present within this problem, so this term disappears, and so does the 1/2 kx final term. And that's because we don't have a spring at either juncture within this problem. We do have an initial velocity in phase B, and that's because immediately following the collision, the system does have a velocity. And of course, this velocity is the final velocity in phase A, and it also serves as the initial velocity in phase B. On the right-hand side, we certainly have an elevation at the end of phase B, so this term does not disappear. However, at maximum height, the system has no velocity. There's the maximum height, and once we attain maximum height, the final velocity equals 0 at that point. And so this term disappears. As a result, the equation reduces to 1/2 mv initial squared just equals mgy final on the other side. 4 terms disappeared, only these 2 terms remain. Now, we have the same mass, basically the mass of the system, appearing on the left and right side of the equation, and therefore we can cancel that mass. And the equation reduces further to 1/2 v initial squared equals g times y final. Now, of course, g equals 9.8, and the final elevation equals 6 centimeters, which we'll enter as meters. So the 6 centimeters will be entered as 0.06 meters. And so on the right-hand side, we have a result of 0.588. We're going to multiply both sides by 2 now. And that equals 1.176. And finally, if we take the square root of both sides, we obtain a result of 1.084 meters per second. Now that is the initial velocity in phase B. And we'll make a note that V initial in phase B actually equals V final in phase A. So let's return now to where we left off within phase A. In phase A, we left off with equation number 1, which states V1 initial equals 81 times V final. Of course, 1.084 equals V final in phase A, so we can just roll this value into our equation. And as a result, V1 initial equals 87.8 meters per second. So that is the initial velocity of the bullet just before it collides with the wooden block. In part B, we would like to determine the amount of energy lost by the system. And so we want to find the change in energy. And the change in energy can be determined by considering the final energy minus the initial energy. So let's take a look at the diagram. This portion of the diagram depicts the initial state of the system. And according to this diagram, the only object that has any type of energy is the bullet, because it's traveling with a velocity of V1 initial. The block is stationary, and also let's note that the block is located at the zero reference height, and so the block has no gravitational potential energy. So initially, we only have the kinetic energy of the bullet. Let's consider the system's final energy content. Now, this diagram represents the system in its final state. And we can note that the system is not moving because it reached maximum height, and so there's no kinetic energy. However, the system is elevated by 6 centimeters above the zero reference height. Therefore, the system has gravitational potential energy, and we're going to consider both of these energies in our analysis. And so, as we noted, the final energy of the system is just the gravitational potential energy of the system, and of course we can note that as PEG final. The system only had initial kinetic energy, and so we can note that as KE initial. Now, PEG final equals MGY final. And which mass should we be using in relation to the final potential energy of the system? Well, since both of the masses are joined together, M refers to M1 plus M2. The kinetic energy is given by 1/2 mv initial squared. Now, it's important to note that only the bullet has velocity at the beginning of the problem. Therefore, it is the only object that has kinetic energy. And this m, therefore, refers to the bullet, which is just m1. So the equation becomes m1 plus m2 g times y final minus 1/2 m1, and the bullet's initial velocity was noted as v1 initial. So let's substitute the values. m1 is 0.025, m2 equals 2 kilograms, of course g equals 9.8, and the final elevation was 6 centimeters, which we'll enter as 0.06, minus m1 is the bullet's mass, which is 0.025, and the initial velocity of the bullet was calculated as 87.8. Let's not forget to square that. If we enter these values into our calculator, we obtain 1.191 minus 96.36, which results in a loss of 95.17 joules. And that is the amount of energy that was lost due to the collision. And that completes this lecture.